In this video, we're going to learn some new trigonometric identities called the sum and difference formulas, and then we're going to do a bunch of different examples applying these formulas. So let's start with writing down the definitions. We have different formulas for sine, cosine, and tangent. So I'm going to start with the sine formulas. We have that the sine of u plus or minus v is equal to sine of u times cosine of v plus or minus cosine of u times sine of v. Now, if it's a plus inside the parentheses originally, it's going to stay a plus in the formula. If it's a minus in the parentheses originally, it's going to be a minus in the formula. But all we have to do then is just split this up into sine of u and cosine of v, cosine of u and sine v, add or subtract in the middle appropriately. This formula allows us to calculate exact values for different areas that or different angles that are not directly on our unit circle, not one of our special angles. Maybe we can write them as a sum or a difference of our special angles, so we can write it this way and get an exact number. Now, the cosine formula is a little more complicated. For cosine, we get that cosine of u plus or minus v is equal to cosine of u times cosine of v minus or plus sine of u times sine of v. Now, notice here I have my plus or minus symbol upside down. That is on purpose. If I have a plus inside the parentheses originally, I'm going to need a minus in my formula. If I have a minus inside the parentheses originally, I need a plus in this formula. So it changes the order, which is why I wrote it as a minus plus instead of a plus or minus. That's probably what makes this one a little more complicated, is remembering that the sign has to change in the middle. Then our tangent formula, we have tangent of u plus or minus v is equal to tangent of u plus or minus tangent of v, all divided by 1 minus or plus tangent of u times tangent of v. This is by far the most complicated of the sum or difference formulas. Notice that when there's a plus inside the parentheses originally, I'll have a plus in the numerator, but I'm going to have a minus in the denominator. And when I have a minus in the parentheses originally, a minus in the numerator and a plus in the denominator. So you have to be careful with that. All right, so now let's use these formulas to do a variety of different problems. And we're going to start by finding the exact value of some various trig functions. Our first one is sine of 195 degrees. Now, 195 degrees is not one of our special angles on the unit circle, so I don't know what this exact value is at this point. You could type it into a calculator, but you'll get some long decimal and not be able to write an exact value based on your calculator answer. However, we can write 195 as the sum of two of our special angles on the unit circle, and then use our sum and difference formula that we just learned. So 195 is the same thing as 135 degrees plus 60 degrees. And 135 degrees and 60 degrees are both some of our special values on that unit circle. So we should know the sine and cosine of those values based on memorizing our unit circle. Now I'm going to apply my sum or difference formula for sine, and I get sine of 135 degrees times cosine of 60 degrees plus cosine of 135 degrees times sine of 60 degrees. And now I can just use the values on my unit circle and simplify to get an exact value. Sine of 135 degrees using our unit circle is the square root of 2 over 2. Cosine of 60 degrees is 1/2. Cosine of 135 is negative square root of 2 over 2. And sine of 60 degrees is square root of 3 over 2. And now I just have to simplify this. Well, in the denominator for both of these, I'm going to have a 4, and then I can just add my fractions together to get my most simplified possible answer. So I'm going to have a square root of 2 minus the square root of 2 times square root of 3, which is square root of 6. So square root of 2 minus the square root of 6, all over 4, and that is the exact value for sine of 195 degrees. So now we can have an exact value just by using our sum and difference formulas and our unit circle. Let's do another one of these, but we're going to use cosine this time. And we'll use radians just for fun. So we have cosine of 5 pi over 12. 5 pi over 12 is not one of the values on my unit circle, but I can write it as a sum of values on the unit circle. So first, notice that 5 pi over 12 is the same thing as 3 pi over 12 plus 2 pi over 12. And I know right now that doesn't look like values on our unit circle, but they are. They're just not simplified. 3 pi over 12 is the same thing as pi over 4. 2 pi over 12 is pi over 6. So I have cosine of pi over 4 plus pi over 6, and that is equal to my original cosine of 5 pi over 12. Now, using my sum or difference formula, I know that I'm going to have this is equal to cosine pi over 4 times cosine of pi over 6 minus sine of pi over 4 times sine of pi over 6. Remember that the sign in the middle is the opposite of what we had in the parentheses when you're using the cosine formula. Now, evaluating this using my unit circle, cosine of pi over 4 is square root of 2 over 2. Cosine of pi over 6 is square root of 3 over 2. Sine of pi over 4, square root of 2 over 2. Sine of pi over 6 is 1/2. So I would have a common denominator of 4 on both of these, and I can just write my simplified final answer as a square root of 6 minus a square root of 2 all over 4. And that's the exact value of cosine of 5 pi over 12. All right, so that shows you how these sum and difference formulas can actually come in handy. So now we're able to get exact values for our trig functions when we weren't able to before. Let's do another example. Let's find the exact value of cosine of 99 degrees times cosine of 36 degrees minus sine of 99 degrees times sine of 36 degrees. Now this one's a little bit different than the ones we just did. We're still going to use our sum and difference formulas, but we're using them backwards. If you take a look at what we have here, I have two angles, 99 degrees and 36 degrees, and I have it written like the right-hand side of one of our sum and difference formulas. This comes from the cosine sum and difference formula, and since I have a minus in the middle, it would be a plus inside of the cosine. So using that formula backwards, I know this should be equal to cosine 99 degrees plus 36 degrees. Well, 99 degrees plus 36 degrees is 135 degrees, and that is one of the values on our unit circle. So using my knowledge of the unit circle, I know that's negative square root 2 over 2. And we were able to get this exact value by using our same sum and difference formula, but in reverse. Now, a slightly more complicated problem. Let's find the exact value of cosine of alpha plus beta, given that sine of alpha is 5 over 13, cosine of beta is 5 over 6, for alpha in quadrant 2 and beta in quadrant 4. Now you can see my cosine of alpha plus beta, we're going to want to use that sum or difference formula to do it. But in order to use my sum and difference formula, I'm going to need to know what sine of alpha, sine of beta, cosine of alpha, and cosine of beta are. But they only give me 2 of those values and not the other 2. But we can figure out the other values. So first, let me just write down that I know cosine of alpha plus beta using my formula is going to be cosine alpha, cosine beta, minus sine alpha, sine beta. And at this point, I know what sine alpha is, and I know what cosine of beta is. So right now I have my cosine of beta is 5, 6. So I have 5, 6 times cosine of alpha. And my sine alpha is 5 over 13. So I have 5/13 sine of beta. But I don't know cosine of alpha or sine of beta at this point. We need to figure those out. So how do we figure those out? We use the info they gave us and the quadrants that these angles are in. So let's start with the angle alpha. Alpha is in quadrant 2. So it's somewhere over here. And then we know we can make a right triangle to represent the situation. And I know that sine of alpha is 5 over 13. So I know my hypotenuse is 13. And I get 5 as the opposite side. Now, figuring out this other side of the triangle, we would need to use the Pythagorean Theorem. 5 squared plus something squared is 13 squared. 25 plus b squared is 169. B squared is 144, and I get b is 12. So I know that this other side of the triangle is 12. Now from here, what would be cosine of alpha? Well, it looks like it should be 12 over 13, but remember, since we're in quadrant 2, it's going to be negative. So I get negative 12 over 13 for my cosine of alpha. We're going to do the same sort of thing to figure out sine of beta. It said my beta was in quadrant 4, so that's somewhere over here. Make a right triangle. And I have that cosine of beta was 5 over 6. So this side is 5, and my hypotenuse is 6. I'm doing the Pythagorean Theorem again. 5 squared plus b squared is 6 squared. 25 plus b squared is 36. B squared is 11. So b is the square root of 11. I know this other side then is the square root of 11. And that tells me sine of beta is the opposite square root of 11 over the hypotenuse, which is 6. But since I'm in quadrant 4, it's negative because my y values are negative in that quadrant. So now that I have my cosine alpha and my sine beta, I can plug those in and get my simplified answer. So where we were at, we had our 5, 6, and then I need my cosine of alpha, which is negative 12 over 13. And then I had my 5 over 13 for sine alpha, and my sine beta is negative square root of 11 over 6. So now I can simplify this. In the denominators, I have 13 times 6, which is 78. So I have a negative 60 over 78 plus 5 square root 11 over 78. And I can combine those together to write my final answer of negative 60 plus 5 square root of 11 all over 78. And that's the answer to my cosine alpha plus beta without even knowing exactly what the angles alpha and beta are. All right, let's just keep doing some more of these examples. They get easier the more you do, so it's good to get a lot of practice in. Let's find cosine of sine inverse of negative 12 over 37 plus tangent inverse of 5 over 12. So that looks pretty terrifying right now, but it really is just the cosine of a u plus a v. We just have to figure out more information on what u and v are. So I'm going to say, let's have u represent the sine inverse of negative 12 over 37. And we're going to have v represent tangent inverse of 5 over 12. So this side tells me that sine of u is equal to negative 12 over 37. And this side tells me tangent of v is equal to 5/12. So now we have to figure out what the whole triangle looks like. So if sine of u is negative 12 over 37, I'm going to be somewhere where my sine is negative. Now remember, my sine inverse gives us values between negative pi over 2 and positive pi over 2. So the fact that it's negative tells me it's somewhere down here in quadrant 4. Let me make a triangle. And I'm going to have my sine is 12 over 37, and it's negative because it's in quadrant 4. Now, to figure out the other side of this triangle, you would use the Pythagorean Theorem again. 12 squared plus something squared is 37 squared. I'm going to trust you to do that arithmetic, and you will get that that other side is 35 if you do that correctly. For the tangent, I have my tangent is positive, and that tells me it's going to be in this first quadrant based on what's the acceptable range for my tangent inverse. So here's my v. Tangent is opposite over adjacent. So I have 5 and 12. My hypotenuse ends up being 13, again using the Pythagorean Theorem. And now we have all the information that we need. I'm just going to leave my pictures of the triangles up because we're going to need those. And what I'm trying to find is cosine of u plus v. U is equal to the sine inverse of negative 12 over 37, and v was tangent inverse 5 over 12. Using my sum or difference formulas, this is cosine of u times cosine of v minus sine of u times sine of v. And now I can just use my triangles to figure out this information. Cosine of u is positive in the fourth quadrant, and cosine would be adjacent over hypotenuse. So I get 35 over 37. My cosine of v is also positive in the first quadrant, and I get my adjacent over the hypotenuse, which is 12 over 13. my sine of u using this triangle or the info we had before is negative 12 over 37. And sine of v is opposite over hypotenuse, that's 5 over 13. And now I just have to simplify this. I have minus and negative, so it's going to be positive. My denominators are both 37 times 13, which is equal to 481. So this is equal to 35 times 12, which is 420, over 481, plus 12 times 5, which is 60, over 481. Combine them together to get 480 over 481 as our final answer. So this one was much more complicated. It still came down to just using our sum and difference formula, but we had to remember things about the inverse trig functions to set up the triangles in the appropriate quadrants. So we've done a lot with the sine and cosine sum or difference formulas, but we have not yet used that tangent sum or difference formula. So let's do an example where we have to use that tangent formula. Find the exact value of tangent of 165 degrees. So I'm going to want to rewrite this using my special angles from the unit circle again, because even though we don't read tangent directly from the unit circle, we know tangent sine over cosine, and I know my sine and cosine values from my unit circle. So tangent of 165, I can rewrite that as tangent of 135 degrees plus 30 degrees, and both of those angles are on my unit circle. So now using my sum or difference formula, I get this is equal to tangent of 135 degrees plus tangent of 30 degrees divided by 1 minus tangent of 135 degrees times tangent of 30 degrees. And now I just have to use information from my unit circle. So at 135 degrees, my sine is square root of 2 over 2, and my cosine is negative square root of 2 over 2. So tangent, which is sine over cosine, would simplify to negative 1. For my tangent of 30 degrees, my sine of 30 degrees is equal to 1/2, and my cosine of 30 degrees is square root of 3 over 2. That simplifies to 1 over the square root of 3, which is the same thing as square root of 3 over 3. Then down on the bottom, I'm going to have 1 minus my same values, negative 1 times square root 3 over 3. So on the top, I have negative 1 plus square root 3 over 3. And in the bottom, I have 1 plus square root 3 over 3. And we can simplify this a little bit more still. First thing I would do is get common denominators for both the top of my fraction and the bottom of my fraction. That common denominator for both of those would be 3. So I can rewrite the top as negative 3 plus square root 3 over 3. And I can rewrite the bottom as 3 plus square root 3 over 3. Now, if I flip and multiply by the reciprocal of the bottom, this simplifies to negative 3 plus square root 3 over positive 3 plus square root 3. And that's technically the answer, but let's rationalize our denominator to try to make it a little simpler. So to rationalize the denominator, I'm going to have to multiply both the numerator and the denominator by the conjugate of the denominator. And then you have to do a bunch of distribution to get the proper answer. If If I distribute on the top and combine my like terms, I get negative 9 plus 6 square root 3 minus 3 over, and in the bottom, I get 9 and minus 3. And I can simplify more. Negative 9 minus 3 is negative 12 plus 6 square root 3 all over 6. And then I can simplify by canceling out a 6. So the fully simplified version of the answer is negative 2 plus a square root of 3. And that is equal to my original problem, which was tangent of 165 degrees. We were able to find that by rewriting it as tangent of the sum of two angles that are on our unit circle, and then plug in the appropriate values that we get for tangent of those values using my sum or difference formula. All right. Now, these sum or difference formulas can also be used to prove different other identities. So let's do an example of that. We are going to verify the co-function identity cosine of 3 pi over 2 minus theta is equal to negative sine of theta. And we're going to use our sum or difference formulas to prove this. Just like we did in the last video when we were proving different identities, I'm going to start with the left-hand side and manipulate it to see if I can get the right-hand side. So starting with my left-hand side, cosine of 3 pi over 2 minus theta, using my sum or difference formula for cosine, is equal to cosine of 3 pi over 2 times cosine of theta plus sine of 3 pi over 2 times sine of theta. Now, using my unit circle, cosine of 3 pi over 2 is 0. And sine of 3 pi over 2 is negative 1. So 0 times cosine theta is 0. Negative 1 times sine theta is negative sine of theta, verifying the identity. I got the right-hand side just by using the sum or difference formula on my left-hand side. Let's do another identity verification using our sum and difference formulas. Let's verify that sine of x plus y minus sine of x minus y is equal to 2 cosine of x times sine of y. And just like I did before, I'm going to start with the left-hand side, use my sum or difference identities, and see if I can get the right-hand side. So starting with my left-hand side, sine of x plus y minus sine of x minus y, I can use my sum or difference formula for sine. I get sine of x cosine of y plus cosine of x sine of y. And then I need to subtract what I get for the sum or difference formula for sine of x minus y. That is sine of x cosine y minus cosine x sine y. And so now I would have sine x cosine y plus cosine x sine y minus sine x cosine y, so that cancels out that first term, and then minus a negative, so plus cosine x sine y. So I have cosine x sine y plus cosine x sine y. And my sine x cosine y terms disappeared. They went to 0. They subtracted away. These two guys are the same thing, so I can add them together to get 2 cosine x sine y, which is exactly equal to that right-hand side that I was trying to show. So that formula checked out using just my sum or difference formulas. Now, one last thing that we can do with these sum or difference formulas is rewriting an expression that looks like a number times sine plus a number times cosine into an expression that just contains a sum. So for real numbers, a, b, and x, a times sine of x plus b times cosine of x is equal to some k times sine of x plus alpha, where k is defined as the square root of a squared plus b squared, and alpha satisfies cosine of alpha equals a over k, and sine of alpha equals b over k. And this is true all the time for all real numbers a, b, and x. So I'm going to do an example where we use this information to rewrite some combination of sine and cosine in the form k sine of x plus alpha. So let's write -4 sine x plus 3 cosine x in the form k times sine of x plus alpha. So the first thing I would do is find k. I know k is supposed to be the square root of a squared plus b squared. My a is -4, and my b is 3. So k is equal to the square root of 16 plus 9. That's the square root of 25, which is 5. So I have my k as 5, and now I need to find alpha. I know cosine of alpha is supposed to be equal to my a, which is -4, over k, which is 5. And I know my sine of alpha is supposed to be b, which is 3, over k, which is 5. So let me draw a picture where alpha has to be. Well, my sine is going to be positive, so it's somewhere up in this upper half. But my cosine is negative, so that means I have to be over here in quadrant 2. So my alpha is over here in quadrant 2, hypotenuse is 5, opposite 3, adjacent 4. And the important thing is, in order to find alpha, I'm going to need to use an inverse trig function. Now, my inverse sine function is defined between -π/2 and π/2. My alpha is not in there, so if I used my calculator to find sine inverse of alpha, it's not going to give me a value corresponding to this alpha. It would need adjusting. But my cosine inverse is defined between 0 and pi. That includes where alpha is. So I can do cosine inverse of -4/5 to get alpha. If you just type that into your calculator, I get alpha is approximately 2.498 radians. And that means if I'm going to write my original expression, which was -4 sine of x plus 3 cosine x in the form k times sine of x plus alpha, I get my k, which was 5, times sine of x plus 2.498 in radians. And that is the final answer for that one. If you have any questions, feel free to drop them below. I hope you enjoyed the sum and difference formulas. I actually think they're kind of nice for simplifying things. If you're a current student of mine, you can also ask me questions in office hours, email, or in class. And I'll see you guys for our next video, which is on double angle, power reducing, and half angle trig identities.